Morning, everyone. So we're going to continue our bonding chapter. Pretty much, we're just trying to cover our bases here. We're going to actually look at a few different molecules in real life, and we're going to see, similar to the exceptions that we did earlier, where are places that our models so far, our Lewis, our Vesper, our hybridization, SPDF, where are places where our theory so far doesn't actually match up with real life, and how can we treat it as an exception, and how can we actually come up with a fix of my model so that it's actually consistent with what we see in actual life. So this sort of fix here, we're going to look at a guy called resonance. Once we kind of work through what resonance is, we're going to work through a case study of ozone. It's a molecule that shows resonance here. It becomes a sort of global problem of sort of ozone depletion. We're losing our ozone layer, and we'll get into that as sort of a real world problem. Just before we get into that lesson here, make sure you are practicing a lot of this here. Again, a lot of this chapter here start off with the Lewis diagram, so you want to make sure you're really comfortable with Lewis. Let's do a warm-up question just so that we can practice here. I want you to imagine drawing for me here 3 molecules. Draw for me the molecules NO2, draw for me the molecule NO2+, and the molecule NO2-. So again, you can't do any Vesper hybridizing shape or any bond angle or anything like that without actually drawing the molecule. This molecule here is very similar to the N2O molecule we saw. Back a couple of days ago, we said N2O, strangely enough, it's actually asymmetrical. We have to do formal charges and whatever. This one here is actually NO2, so it's actually a different molecule. This one, there's no real hard ship to it. This one here, nitrogen is the least electronegative. I'd imagine the nitrogen is going to be in the middle. Let's just follow through your Lewis structures here. The N has 5 valence electrons, oxygen is 6 times 2. This one has 17. The NO2 having become a positive is now lost an electron. The more positive I get, I lose one. The more negative I get, another person arrives at your hotel, you have one more. Normally when you do Lewis models, you expect electrons to be paired, so we expect everything to at least have a full octet. We're going to see a radical in this example. We'll come back to this. And I just want to emphasize here, it could be a typical multiple choice question. They might give you these 3 molecules, and they might just say here, arrange by increasing bond angle. So bond angle is sort of the number of degrees between the bonding orbitals that we have. Increasing just means go from the smallest and then go to the biggest. So you notice the question is not, oh, by the way, start off with Lewis and do the. The question is just asking bond angle. We can't answer the bond angle question without knowing the geometries. We can't answer the geometry question without doing the Lewis, which is why I want to emphasize, make sure you're really good at doing your Lewis structures. So I'm going to start off with a more normal compound here. Let's say NO2+. I plop down the middle atom, connect the outside ones with a single bond, start making the outer guys happy. At that point there, you would have run out of electrons. The N here isn't happy yet. The N only is sharing 2 electrons, 4 electrons. What's going to happen is we're going to actually donate these electrons in. Again, it looks like it's going to be a coordinate bond. Without actually doing a brute force, I don't actually know if it's a coordinate bond or not. This one here is a positive charge, so you do want to put square brackets around it with the charge in the corner. There you go. That's the correct Lewis diagram. Normally, the diagram that you first draw with the least electron in the middle, normally this is going to be the one with the best formal charges anyways. Normally you don't check it, but if I wanted to show you formal charges was this notion of you take the valence electrons that I have, you subtract how many you've drawn on it, and in this case here it actually gives me more information. Nitrogen has 5 valence electrons normally. If I only assume that these bonds here, only one of the electrons of the bonds belong to nitrogen, 5 minus 4, it gives nitrogen that charge of +1. It reminds me that this molecule here is charged positive. It's lost an electron overall. And what formal charges tells me, although this is not a full positive 1 charge, where I would expect the positive density to be in this molecule is more so to the middle, which is consistent with the fact oxygen is more electronegative. If anyone were to be negative, if anyone were to hog the electrons, I'd expect the density to be outside. We'll see a nice electron density map in today's lesson to emphasize that. Let's do the same with NO2-. Again, you sort of get mainly the same sort of picture, 16. In this case here I have 18, so I actually do have 2 extra dots. At that point I completely run out. I know it's very tempting to draw even extra dots after that, but no, I don't have any more electrons in the bag. At that point there, I'm going to squeeze in one side or the other side. This is going to be an example that shows resonance in our lesson, but so far we're going to have, again, this is a negative charge. Having stolen an electron, my type of bonding is actually a little bit different. So there we go, there's my picture. The NO2 with no charge is actually going to be a radical. It's going to be unpaired electron. I know not everyone is going to have a full octet. If I have an odd number, I can't have everyone having 8s. So in this case here, let's just try it out. I gotta have my N. I'm gonna plop down my O's, put down those outer electrons, work your way outside to inside. In this case here, we do have that 1 unpaired electron. Now what we can do is we can say, well, the oxygen here is happy, this oxygen here is happy, the nitrogen is sad. Nitrogen is 2, 4, and actually just 1 there, so nitrogen has 5. I know while I'm not going to be able to get it fully to an octet, I can at least get it closer. Let's bring one of these in, make it a double bond. Remember, there's no chemistry in those rules. That one may or may not be a dative bond. You need to check it for yourself. But in that case, their nitrogen now thinks it has 7. That's actually the closest it can be. So that actually is the correct diagram here. This is a radical. In fact, what's going to happen here is you're going to emphasize N has an unpaired electron. We're going to have the double bond on one side, and we're going to have the single bond on the other side. Correct Lewis diagram should have all the other dots on there, but I just want to emphasize this nitrogen here has an unpaired electron. Just some notation for you again. That unpaired electron makes this chemical a radical. Sometimes they refer to it as a free radical. It's a radical that's free to go. This radical here is super unstable, super high energy. This is going to try to very quickly try to bond away this unpaired electron. And we're going to see that's actually causing the trouble in today's lesson. Here's where actually an example where formal charges actually gets it wrong. Again, you don't need to check formal charges for every single molecule. I'm trying to give you some examples where formal charges actually helps. If you do formal charges, you're actually going to end up realizing this oxygen here is 6 minus 6, so 0. Nitrogen here is 1, 2, 3, 4. So in this case here is actually 5 minus 4, so it's going to be plus 1. Oxygen is valence of 6, minus off the 1, 2, 3, 4, 5, 6, just 1 in the bond. 6 minus 7 is equal to negative 1. So we have one side plus 1, one side negative 1, just like that middle one. You might imagine, well, what if I just forcefully put the other 2 electrons? What if instead of 7, what if I made it 9? So let's just test the picture. We're still a radical. Let's say we have this one. This one here, formal charge-wise, it actually works better. This one here would be 6 minus, now it's 1, 2, 3, 4, 5, 6. Oh, great. This has 0 charge. Oh, perfect. With that unpaired electron, 5 minus 5 actually gives you 0. The oxygen on the right side also gives you 0. So between these two pictures, based on what we know, we'd say, oh, of course it's this one, because this one here has the least formal charges. As I mentioned here, here's an example where even my formal charge exception gets it wrong. How do I know it gets it wrong? Is nitrogen actually able to expand its octet? Normally we would pull in electrons when I sort of run out of electrons. In this case, I didn't run out. I'm just testing the pictures. You'll get another practice of this on your lab. But if you did this, nitrogen is only row 2. Being on energy level 2 is not a very large shell. I don't have my d orbitals for bonding. I can't hybridize those. You know how the hybridization was sp3d. I don't have any d orbitals. So I know N, being on shell number 2, this one here cannot expand. So this picture here cannot be correct. So that's way just to show you there. Oh, sometimes formal charges also gets it wrong. Just take it with a grain of salt. Sometimes it's good, sometimes it's bad. But back to our question here. Now we've done the Lewis. We can start trying to think about the Vester, trying to think about the bond angle here. You look at the central atom. In this case here, it's nice. It's just the one N atom. This N here happens to only have 2 domains. Hopefully you can say to me, if 2 balloons are pushing away from each other, linear, the bond angle is going to be 180. You can practice that's going to be sp hybridizing. So that's a fairly big bond angle. The other 2 are going to be trigonoplanar. The other 2 have 1, 2, 3 domains. These domains are going to push away from each other here. I'm going to have my more 3D-like picture here. Technically, for a 3D diagram, you don't have to have all the dots. Lewis, you do. In this case here, I know I'm going to be based off of trigonoplanar. Trigonoplanar is supposed to be 120, so triplanar. But remember we said the lone pair here is more diffuse. There's no bonding atom that's sort of confining in space here. This balloon sort of blossoms out and spreads out. It's going to push the leftover bonds a little bit tighter. So in this case here, let's quote a couple degrees smaller, maybe 117 degrees. This radical is sort of crazy as well. It still needs the room for 3 orbitals. So that one there will also be trigonoplanar. But in this case here, because everything else is the same, I would imagine this one electron is not, it is going to be a diffuse balloon, it is going to be a larger balloon, but because there's only 1 electron as opposed to 2, I'd say this is less electron dense. Because it's less electron dense, the amount of squeezing of the bond angles might actually be a little bit less. I might quote here maybe 118, 119. I don't know the exact number, but I might just expect to be less than the other one. So in terms of smallest to biggest, then we had the 117 as the smallest. So my order as my answer, NO2 minus is smaller than NO2 is smaller than NO2 plus. That could be a paper 1 question. You see, it was quite a lot of work. I had to first draw them. I had to do the VSEPR. That's how you want to get really quick with your Lewis practice. All right. So now onto our lesson here. I just mentioned here this NO2 is an example of something that shows resonance. What I mean by resonance, so we're going to focus on just that one formulation here, NO2 minus. I want to just get us back to pretend we were doing the Lewis model. Again, you can access your notes here on the handout section. You can scribble over it with me here. By the time this guy here is 18 total electrons, by the time you draw in your 18, you would have this picture. Sure, it's charged. Don't forget that square bracket with the charge in the corner. Here's the question I want to address to you. Well, the nitrogen here is unhappy. The question here is, what happens if the double bond comes in on the left side? So I get a molecule where the double bond is on this side. Or, if instead of this guy trading it in, what happens if it was this guy traded in? So I had an N double bond on this side. The question here is, are these the same or are they different? Now, there certainly are similarities. They're all made out of N and 2 O's. They have a double bond and a single bond on one side of it. Is it just I'm looking at this blue atom from the front and I sort of go, so this is me in front of the diagram. I walk to behind the diagram and I look from the other side. Oh, of course, the double bond's on the other side. I'm going to sway your vote a little bit. Are these the same? Are these different? If I could paint these, if I can paint the oxygen on the left like a blue highlight, the other one here a green highlight, are they the same now or not? Hopefully you're ready to say that they're different. Having a double bonded to the blue and a single bonded to the blue is different. Single bonded green to double bond green, different. Sure, I have one single bond, one double bond, but these are different molecules. Actually, technically in quantum mechanics, there's something in our universe that says you can't actually do this painting, but that's just for easy understanding. So, a molecule like this, where it's possible it could have been the double bond on this side, it could have been the double bond on this side, the double bond could have been in multiple places, we say that this molecule shows resonance. We know molecules show resonance if there's more than one possible valid Lewis structure. We could have been this one, we could have been this one. We call each one of these possible drawings a resonance form. So one of many alternative diagrams. Sometimes you have 2 resonance forms, sometimes you have 5 resonance forms. It's just any given picture that you can draw for it. Long story short here, things that show resonance, unfortunately, we actually have to draw all the resonance forms, and we have to connect them with the double-headed arrow. So we're going to see that as we kind of move on here. Here's the kicker. Not only do I recognize this one here shows resonance, not everything shows resonance, but molecules like this that show resonance, none of these resonance forms are actually correct. So why bother drawing it if it's not correct? These are purely hypothetical ones that do not exist. They're hypothetical in the fact that sometimes the double bond is in one place, sometimes the double bond is in the other place. So I've just resketched those molecules for you. Could the double bond be on the left side or could the double bond be on the right side? Again, this is us going in nature, measuring it in real life, seeing whether it fits or doesn't fit. We're saying, nope, it actually doesn't fit. Here's what it looks like in real life. Experimentally, this N2O molecule here, the 2 bonds on either sides are actually equal. They're equal in what? They're equal in terms of length. If we really were a double bond and a single bond here, we would have expected a long single bond here, only 2 electrons, not really pulling in the centers too tightly, 4 electrons which pull in tighter. I'd expect this molecule to be slightly demented, short on one side, long on the other side, and yet in real life we see that because of resonance, these actually show an intermediate length. They're actually halfway. They're a little bit shorter than a single, but not quite short enough to be a double. And similarly with strength, I expect a single bond to be weaker, double bond to be stronger. It has somewhere intermediary, somewhere in the middle of strength. So again, this is us just sort of covering our bases here. Well, we know what it looks like in real life. We see our limitations with Lewis. This is actually how you would answer your question. You'd say, okay, draw this molecule here. Well, it could be this form, it could be this form. These are actually in resonance. The real diagram, we can call that there the resonance hybrid. They don't always ask you to draw the resonance hybrid. The real diagram has an N. It is definitely connected to the 2 O's. But what's happening here is, instead of really being able to pinpoint, the electrons are either on the left side making the double bond on this side, or they're either on the right side, they're actually not localized, they actually are delocalized. these electrons are actually swimming around the entire picture. They're actually shared by all three centers. So we're referring to these ones here as delocalized electrons. See if you can remember where else in the course we talked about delocalized electrons. Here's another example of it. This basically just means here we have these two electrons. Instead of really being to put your finger, you're on left side or right side, they're actually shared by all centers. Shared by every center. The only problem here is Lewis doesn't let us do this. If I try to do a resonance hybrid, if I try to do like an and then like a dashed line here, that's how I would draw the hybrid. I would be like, well, what is that? Right? Is that a single bond or is that a double bond? Truly speaking here, it's somewhere in between. Now, while I have the diagram on there, because we are completely shared, we come up with another tool. This tool here is what we call the bond order. The bond order is a number that you can associate to actually talk about once the sharing has happened, how many bonds you actually have. So something that has a bond order of 1 is just a single bond. Something with a bond order of 2 is referred to as a double bond. In this case here, how are you going to find this bond order? This time you're going to look at the number of electron pairs. Look at the central atom. How many electron pairs am I potentially sharing? So if I look at the Lewis diagram here, I had an N, I had a double bond seemingly on one side, a single bond on this side. I am trying to share 1, 2, 3 pairs. Notice we're not talking about domains this time. This one would have only been sort of 2 domains as I highlighted there. But in this case here, I'm looking for how many pairs I'm actually sharing. I'm trying to share 3 electrons, and I'm trying to divvy it out over 2 different directions. My bond order, the number to describe how strong the bond is actually 1.5, and I'm exactly between a single bond and a double bond. So this hand-wavy math here tries to figure out here how far between the two, the single bond and the double bond I actually have. I may come to other molecules later on. Maybe I'm sharing 4 over 3 different directions. I have a bond order 1.33. Also somewhere between a single and a double bond, but a 1.33 bond will be weaker than 1.5. It's also going to be longer than 1.5. In general, as you go single to double, we're going to slowly get stronger as bonds. We're also going to get shorter as bonds. Wherever I am along the spectrum tells me somewhere intermediate in terms of strength, in terms of length. So that's what resonance is. First thing I want to emphasize again, not everything shows resonance. You will only have resonance when, as we're drawing a Lewis picture here, it could have been this one double bond, it could have been this one double bond. We're limited in terms of Lewis structures here. If that's the case, you draw every single hypothetical structure, every single resonance form, and the understanding is it's like hybridizing again, but we're not hybridizing orbitals this time. We're actually hybridizing the 2 pictures together. The real molecule is somewhere in between, some average of these 2 pictures. In fact, we said neither of these resonance forms actually captures it. So let me give you an analogy here. Let's pretend I've never seen a dragon before. Well, it shouldn't be that hard to imagine. I haven't seen a dragon before. If you were to describe to me what does a dragon look like, you might say to me things like, the dragon may have wings like a bird. And the dragon, breathes fire like a lizard. Something like that, right? So, is a dragon actually a bird? No. Is the dragon actually a lizard? No. But the dragon, this resonance hybrid, is going to be some combination. It has some aspects of bird, some aspects of lizard or horse or whatever animal you want to throw in the mix there. So, although we're having to draw all the little bits, we're like, okay, it's characteristics of the bird, it's the characteristics of the lizard. We know the real picture is actually the dragon. And remember, the dragon is just sitting there minding its own business being the dragon. It's not half the time it's a bird and then it gets bored and then it transforms into a lizard. No, the dragon is just sitting to be the dragon. We're just limited in how to describe that dragon, and we're having to describe it with these purely hypothetical structures. And we're just sort of demonstrating that our real picture, our real dragon, has characteristics of the bird and the lizard, but it's some combination, some average between those two. The textbook uses a very similar analogy here. It uses the mule as a cross between a donkey and a horse. The mule is just minding his own business, just being the mule. It's a cross between a donkey and a horse, so it has characteristics of both donkey and horse, but it's not flipping. It's not horse half the time, and then when you're not looking, it transforms into a donkey. No, neither of these molecules actually exist, but some average between the two of them represent your dragon, or in this case, represent your mule. So, for molecules that show resonance, especially in your lab, double check in places where you can form the double bond. It could have been here or it could have been here. We're limited to draw all the pictures. We connect them with a double-headed arrow. Next here, we're going to do another double-headed arrow that looks like this. That arrow there stands for equilibrium. So make sure your double-headed arrow here is actually looking like this, and that's actually the resonance arrow. So let's just look at a few other examples of resonance. That's pretty much the technical bit for today's lesson. We like this molecule here, benzene, in organic chemistry here. Normally when I have benzene, so we have 6 carbons. If I had 6 carbons just sort of single bonded, I would expect for every carbon that has 4 valence electrons, for 4 arms, I would expect actually a ton of hydrogens. If you actually counted out all of them, you'd actually expect it to be C6H14. And yet when benzene forms a molecule, it's only C6H6. It's managed to keep all the carbons, but it's managed to ditch a bunch of the hydrogens. We're going to learn next year, this is referred to as hydrogen deficiency. I'm actually getting some unsaturation because I'm losing hydrogens. There's 2 ways to lose hydrogens here. One way here, this is getting a little bit organic. One way here is to make a multiple bond. If I start making double bonds and triple bonds, I'm going to start losing hydrogens. And the other way here, where you see in our organic, is if we start making rings. Technically, the molecule can be made out of any number of rings, but for simplicity, we're only going to deal with 1-ringed molecules. So you see benzene actually has this sort of best of both worlds. It has the ring. It actually has 3 double bonds. Every time I form one of those, I end up losing some hydrogens. Benzene always looks to me like a turtle. In fact, we're going to draw it with a skeletal structure later on. The corners represent carbons. So we have sort of carbons in a hexagon ring. I do have double bonds. Oh, wait. The double bonds could be sort of top left, bottom left, right. Or it could be just on the left side, right side, and down this way. Because the double bonds can be multiple places, we're actually going to say this shows resonance. We're limited by saying this is not the right picture, this is not the right picture. The real picture is somewhere in between. We're going to use that hybridization that we learned from previous lesson here. Every carbon center is trigonoplanar. If you can say trigonoplanar, you should be able to say 120 degrees. 120 degrees here would be hybridized sp2. So what's happening here is we're going sp2, sp2, sp2. The carbon on the next side also sp2, sp2, sp2. This bond here is going to be along the internuclear axis, so that's a sigma bond. Where does the seeming double bond actually show up? We knew that when I had a double bond, it's actually a pi bond. So the pi bond is actually the p orbital that goes up and down like this. We're going to have the equivalent of 3 pi bonds. Overlap above and below is just 1 pi bond. And there we go. We get a perfectly flat structure. This one here is perfectly planar, unlike our molecule from yesterday. And in this case here, we have the equivalent of 3 pi bonds worth. But because we're planar and these carbons are actually really close together, we say because of resonance, these electrons are not actually localized. You can't actually put your finger on, aha, the electrons are here or here or here. What we're going to actually see is the electrons are actually spread over the entire map. So these electrons in the pi bond are actually able to swim around the top or swim around the bottom. There would be the equivalent of 6 electrons doing the swimming. They're perfectly delocalized. That's why this electron density map here might be a little bit nicer. This sort of ring diagram here. That's why with benzene, instead of drawing this sort of the double, single, double, we usually just draw it with a circle, just to show you that the electrons are actually delocalized. They're shared evenly around all these centers. This last picture here is a nice electron density map. It actually shows you places that are positive, places that are negative. The places that are sort of the greenish or yellowish, you can sort of see which side is more negative, which side is more positive. Unlike seeing, you see where the electrons would have shown up would be this sort of yellow region. Unlike seeing the yellows actually show up, oh, it's just yellow there, it's just yellow there, it's just yellow there, for where the double ones actually are, you see that the yellow is actually evenly shared amongst the entire ring. That actually implies to you that this shows resonance. So let's just read through here. The pi electrons actually do not belong to any given center. You can't really put your finger on where the electrons are. Rather than being confined, they're actually spread evenly. They're delocalized over the centers. Molecules like benzene demonstrate this property called conjugation. Conjugation has this practice of alternating single, double, single, double, single, double. We're going to learn next year that actually allows it to actually absorb radiation. And we also refer to this one here because electrons are in these p orbitals and they can actually swim around the picture. Benzene is going to be electrically conductive. We actually refer to this sort of, put this two together here. We can call this one here a pi delocalization because it's equivalent of what would have been pi bonds, but they are delocalized in resonance. They are shared evenly by the different centers here. Let's just try this next molecule here. This is a nice molecule to practice Lewis. Be really careful counting the total number of electrons. So we have 1, 4, Oxygen is 6 times 3. Careful, there is a minus there, so there's one extra one. This one here should have 5. We should have 24 electrons. Try drawing this molecule for yourself. Maybe pause it and see if you can do it. At first, you may have tried to do this, right? Based on our Lewis structure rules, why not? Okay. If you're keeping a good hold on the number of electrons, you're going to actually realize we run out of electrons at this point. So if I've used 8 this way, 8 this way, I've used 6, 8, so I've used up all 24, but in this case here I've run out. Now we have run out in the past, no problem, let's make a multiple bond. The trouble here is, where do I make the multiple bond? If I made a multiple bond that has nothing to do with that oxygen there, that double bond there doesn't actually help this oxygen here, let alone carbon cannot expand. If I tried to make the double bond where it mattered, let's say this one here, oh, it shares in the electrons, well, the oxygen is no happier, and again, the carbon cannot work. So it's not a problem with you, oh, you're really terrible at doing Lewis structures. It's just a harder molecule to draw. Hopefully you were able to find the solution here. Actually, technically, before we get to the solution, we could hypothetically stretch this lone pair here. I can make that data bond across. That's possible. Again, 4 more charges gets it wrong in this picture. This would have no 4 more charges, except for the -1 here. But what we're going to see in our organic chemistry, because these bonds here all imply that there's electrons, when we start stretching it at such narrow angles, right, this triangle angle here, we'd be at orders of 50 degrees, 60 degrees or so. That ring is so tight that this one here will be super unstable. So none of those solutions actually end up working out. Turns out the solution is, let's try out a different basic structure. It doesn't all have to be, say, surrounding the carbon. Let's reattach the hydrogen, let's say, to the oxygen instead. So let's try it out here. So I have carbon. Let's try the hydrogen in a different place here. So far I've used 2, 4, 6, 8. Work your way outside to inside. 10, 12, 14, 16, 18, 20, 22, 24. In that case, I still ran out of electrons, but because the hydrogen is now in a different spot, we actually can make those double bonds and actually make it work. So for example, I could have been this one here making the double bond. It could have been that one here on top. This one here is in resonance with, what if it was the carbon on the right hand side that actually made the double bond? So carbon, again, this is a little bit tedious because I'm having to draw all the possibilities. And I'm saying that although none of these pictures here are actually the correct diagram, the real diagram is actually some combination somewhere in between. In this case here, they actually have 3 resonance forms. You just need to look at your molecule to see how many that you would have. And here's a nice general comment here. Resonance adds stability. Molecules that have resonance are going to be more stable because the electrons are delocalized. The electrons are actually shared. I'm thinking the molecule here, my dragon, is actually going to have a bunch of electrons that are shared between these centers evenly, right? It's not actually shared past that. But in this case here, we see from 4 more charges, not each of these structures contribute to the full diagram. Maybe let's do this in full detail here. Not every diagram is actually going to be equally stable. If you check your 4 more charges, this one here has that negative. You have definitely stolen a negative from someone, so that charge has to be accounted for somewhere. It's evenly distributing there. In this case here, the 4 more charges are a lot worse, -1, -1, +1. In this case here, we'd say, yeah, having 3 is good. It gives you the added stability, but I expect this one here would contribute less to the real picture because this one here has bigger 4 more charges. So having the 3 is good, but one of these pictures here is not as good as the other 2. What's the bond order here? So just focusing on the carbon here, I have the equivalent of 1, 2, 3, 4 bonds. Again, not domains. I have 4 bonds worth. I'm sharing it in 3 different directions. Here's an example of a molecule that shows 1.33. Yes, somewhere between single and double, but this would even be weaker than that 1.5 bond we saw earlier. Again, not every molecule shows resonance, but if it does show resonance, you do need to draw all the hypothetical pictures. Let's just switch gears here and actually look at a case study. This is how it actually applies in real life. You can try drawing ozone. Ozone is the molecule O3. If on the test here, a nice hint, if I say draw ozone, don't say which ozone. You might be thinking oxygen. Oxygen is actually just a double bond. So oxygen is O2. For ozone, just like our NO2 atom we drew earlier, we're going to find by the time you get to this picture, we run out of electrons. And because of that, we could have been the double bond on the left side in resonance with, it could have been the double bond on the right side as well. So again, we're limited. We can't draw the resonance hybrid unless we're asked for. The bond order would be 1.5, just like earlier, 3 divided by 2. So the bond strength is 1.5, whereas oxygen, always O2, has a bond order of 2. So we see that the oxygen bond is actually a little bit stronger. Case study here, ozone and oxygen are both important in protecting us from the UV radiation from the sun. The ozone layer is a region in the lower atmosphere called the stratosphere, 12 to 50 kilometers. There's a layer above our Earth that actually has a very high concentration of ozone. But when we mean high, it's actually really small anyways. High still means 10 parts per million. For every million air molecules, you may have 10, or they just say 1 in 100,000. So what I'm picturing here is we have our Earth. We have our sun that's giving us our UV radiation here. There is a region of the stratosphere here. We call it the ozone layer. It has 10 parts per million ozone, give or take. And that ozone layer, although that number here is not very high, it's the sort of the most concentrated layer. What's going to happen here is the sun is going to shine a bunch of UV radiation. It's going to send in a whole bunch of different energies. We're going to categorize. We know UV started from about 400. We're starting to get more energy. And what we're categorizing here is we're separating, well, between 320 and 420 in terms of wavelength. It's called UVA, stronger and stronger for B and C. So low, medium, high in terms of energy. If we're really high energy, it's strong enough to even rip apart a strong bond order 2. So the really strong stuff is actually being absorbed. The oxygen over here will take away some of this really, really strong UV-C radiation here. The oxygen molecule actually separates. It homolytically fizzes. We're going to see on the bottom here. It's going to rip apart. But because this one here has absorbed that UV radiation, that UV-C radiation never really gets down to the Earth. So the oxygen becomes a protective layer for us. Usually when we put on sunscreen here is to protect not against the really, really strong stuff. We're protecting against sort of somewhere between UVA and UVB. So UVB here is going to be somewhere moderate in energy here. The oxygen bond is going to be too strong. A bond order 2, the UVB radiation would just go straight through. It wouldn't actually be absorbed by oxygen. However, for ozone, because the bond order is 1.5, don't tell me one side is stronger, one side is weaker. Remember, the resonance hybrid is actually, it's even on both sides. I have a 1.5 and 1.5. That one there is actually going to soak up some of this UVB radiation. In the same fashion, the ozone breaks up, and therefore the UVB radiation doesn't get through, and here we are on the Earth, and we're protected. The worry here, again, this is going to be a global problem. Some of the sort of industrial stuff that we've been doing has been depleting the ozone layer. We've been sort of eating a hole in this layer here, and if there's not enough ozone, that UVB radiation can come straight through. We have sort of at risk of more sort of radiation poisoning. Hypothetically, we could create ozone, no problem, but it becomes a more like political, who's going to make the ozone, who's going to pay for it. Even if we can manufacture tons of ozone, how can we float it up to a layer? How can we make sure that it stays naturally in the stratosphere here? There's a lot more engineering problems to deal with, but at least that sort of demonstrates a sort of case study with the chemistry of it. So just to mention, again, these are, unfortunately, this is about maybe 70, 80 years ago. Unfortunately, with a lot of our old refrigerants, we use these chlorofluorocarbons. They're made of chlorine, fluorine, and carbon. Unfortunately, these ones here, there were a whole family of molecules. When old refrigerators were tossed out and these gases actually leached out in our atmosphere, these ones here actually artificially destroyed our ozone. So here's what's going to happen. I'm going to imagine having an old refrigerator. I'm going to take one example of something that's a CFC, a chlorofluorocarbon. In the sun's radiation here is going to strike one of these bonds. I actually show you it with the chlorine, just the diatomic molecule. Same thing happens. What the sun's going to do is it's going to homolytically, it's going to do the same, it's a very even split, fizz, so it's going to separate the electrons. 2 electrons make up a bond. I'm going to separate 1 electron to the chlorine on the left, 1 on the chlorine on the right. So same thing happens to my chlorofluorocarbon. Essentially, that bond there breaks. We're going to see in chapter 5, the CCl bond is weaker than CF. So depending on how strong this UV radiation is, it's usually the Cl that happens. In this case here, I know chlorine actually has 7 valence electrons. The important thing to know for chlorine is it has actually an unpaired electron. It's now referred to as a chloride radical. Radicals, like we said, it's super unstable. It's going to try to really quickly pair up this electron. And here's the mechanism. Here's what's going to happen. Chloride actually attacks the ozone in the atmosphere. It's going to form another radical. it converts ozone into oxygen, and then before this reaction is done, this ClO radical reacts with another oxide radical, just produced naturally in the atmosphere, reforms, so radical and radical, they terminate together and they pair up, they become oxygen. They end up reforming the chloride radical again. So here we have a chloride radical. Chloride radical is actually a catalyst. It was put in, and it actually comes out unchanged. Now it's ready to cycle again. It's ready to destroy another ozone. In this case here, we refer to it as a chain reaction because it was put in one step, it gets regenerated, and now it's ready to take out another ozone. One chloride radical before it actually matches up with another chloride radical, actually terminates. One particle can actually destroy thousands and thousands of ozones. We're going to see more of this mechanism stuff in chapter 6 next year, but I've seen them fair game to show me the chloride mechanism for the depletion of ozone. You just need to quote that one there. Another similar radical, not from CFCs, but another radical would be a nitrous oxide radical. I demonstrate to you how it forms, and again, it's a chain reaction. I have an NO radical. It has a bunch of other electrons, but I want to emphasize the fact that it's an unpaired electron. It goes in, and it comes out, and now it's ready to cycle. Overall, the net mechanism doesn't have it show up at all because it gets regenerated and it cycles through this chain mechanism. So I just wanted to introduce to you that notion of resonance. Remember this notion, not everything shows resonance. If you find that, it could be this guy double bonds, it could be this guy double bonds, you have to show all the possible resonance forms. Be careful, none of these forms here actually exist. The real form called the resonance hybrid is going to be this sort of solid line dash diagram. The dash refers to electrons being delocalized, they're being shared over. We can do that bond order to figure out how strong the actual bond is. The hybrid is not constantly flipping between forms. My dragon is not bird half the time, lizard half the time, but my dragon has characteristics. It's some average of it has wings like a bird and it breathes fire like a lizard, right? Lizards don't breathe fire. Okay. But hopefully it helps you memorize it there. If you have any questions, just let me know. Thanks, guys.